Okay. Let's start the class. So, in the previous class, we learned about the cache organization. So, actually, I showed the example of cache organization. Okay. So, as I explained, the address of load instructions or store instructions are split into some field of the cache index or byte offset or cache tab. Okay, so this is the hardware organization of the cache. So as you can see, each entry, so each block of the cache has the data part. So this is obvious that the cache needs to store data temporarily. So cache requires the data field. So data is stored in this field. Also, in order to identify data, so we use the address, but as I mentioned, we can use the part of address, right? So this part of address is called the cache of the cache. And so also, cache requires the control bits. So in this example, this cache has the one valid bit per block. Okay, so this valid bit is required for checking the validity of the stored block in the cache. Also, we learned about the cache write policies. So we learned about the write through policy and write back policy. And then write through policy means that in the write hit case, so which means that the store instruction is executed, then store instruction can update the data in the cache. But as you can see, the block size is usually larger than the size of the data transfer. So which means that when the load word instruction is executed, this load word instruction requests the 4 bytes of data. Okay, but the cache block size is usually larger than the request size. So usually in the commodity CPU, such as the i3, i5, or i7, the block size of the level on cache is the 64 bytes. Okay, it's larger than the request size of the loaded or store instruction. So write through means that in the write hit case, so it means that when the store instruction is executed, the corresponding block is found in the cache. So which means that when the store instruction is executed, then the target data should be updated, right? So write through means that when the store instruction is executed, both the data in the cache and the data in the memory are updated immediately. Okay, which means that we can find the data in the cache and then main memory. And then when the store instruction is executed, then with the store instruction, the data in the cache is updated also at the same time. The data in the memory is also updated. This is the write through policy. But I mentioned that write through policy has disadvantage. Disadvantage of write through policy is that when the store instruction is executed, then with the store instruction, then the data in the memory will be also updated. And then I said that the memory is 0. That's why we use cache. Okay. The memory size is larger than the cache size, but memory is very, very slow. So which means that when the store instruction is executed, then with the store instruction, the processor needs to access slow main memory. So we also calculate the effective CPI by this write through policy. So in order to solve this issue, then we can use the write buffer. Okay, and then write back policy is that and the store instruction is executed, and then in the write heap case, then with the store instruction, the data only in cache is updated. Okay, the data in the memory is not updated immediately. And then I said that when this cache block is deleted from the cache, so because the cache size is smaller than the size of the memory, then the block can be deleted from the cache. Okay. So when this block is deleted from the cache, then this line is updated to the main memory. This is the write back policy. So the data, actually the issues of this write back policy is there. So when the data exists in the cache and in the main memory, then we think that this data is identical. So which means that actually the cache is the temporary space for data. So which means that we believe the data in the cache is same to the data in the memory. But because of the write back policy, the data in the cache can be different from the data in the main memory. So that is the issue of the write back policy. But most of the commodity CPUs employs the write back policy. Okay. And also I explain about the two different policy for write in this case, the allocate or miss write around. Okay. So because the write miss case and the store instruction is executed, the corresponding data is not found in the cache. Okay, so in this case, this is the write miss case. Okay, the store instruction is executed and the data updated by this store instruction is not found in the cache. This is the write miss case. So for the write miss case, allocator, this means that the data is fetched from the main memory, and then this data is allocated to the cache, and then the store instruction is executed. This is the write allocate on miss, and the write around means that the write just update the data, right? So write around means the write execution bypass the cache, okay? Because the data is not found. The data is directly updated on the memory. Okay, this is the write around policy. And then I also explained that for the write back policy, we frequently use the allocate on miss. Okay. Okay. So now, so in this class, so this is the today's class, I will explain about the cache performance. But before starting today's class, so we will take the final exam on December 15th, right? So actually, it was scheduled, the final exam is scheduled on December 15th. And when I introduced about the syllabus, right? But one of the students have the schedule conflict. One of the students has schedule conflict, so I already posted the schedule, the modified schedule about the final exam. So actually, the final exam was scheduled on during the regular class time, so which means that the final exam is scheduled to start at 10:30. But so I posted in the Blackboard the final exam will start at 10. And then the final exam will end 11:30. Right? So if you have any conflict with this modified final exam schedule, let me know immediately. Okay? No conflict? Okay, good. Also, we have only three in-person classes until the final exam. But we missed the one class because of my business trip. So actually, I will record the missed class on Friday, and I will post this class on YouTube on Friday, this Friday. Okay. So we have 4 classes until the final exam. Okay, so let's discuss about the cash performance. Okay, so as I mentioned, actually in chapter 4, we learned about the processor architecture, and then I explained that instruction memory and data memory are actually level caches. Okay, but when we learned about the processor architecture, then we assume that when the load instruction is executed, then the data memory only consumes one cycle. And it's the same for the instruction memory. So when the instruction is fetched from the instruction memory, but actually this is the level of instruction cache, we do not consider about the cache miss cases. So which means that when the instruction is fetched from the instruction memory, the level of instruction cache, then it takes, we assume it will take only one cycle, but it's not true because these memories, the instruction memories and the data memories are cached. Then the requested data can be found in the cache or cannot be found in the cache. Okay, there are 2 cases, there are 2 possible cases. The one, so cache hit case, so this is the good case because the data is found in the cache. So it can only take one cycle for accessing this level of caches. But the cache miss case, so which means that the request data is not found in the cache. And then I explained that when the data is fetched from the low-level cache or main memory, then it will take many cycles. Okay, it depends on the location of data. So if the data is fetched from the level cache, then it will take around tens of cycles. But if the data is fetched from main memory, then it will take hundreds of cycles. Okay, main memory is very decision. So when we consider the performance of our processor, then we also need to consider the performance of cache hierarchy, right? Because there are 2 cases, and the cache is accepted, and hit cases and miss cases. Then we need to also consider these miss cases for considering the performance of our processors. Then actually the hit case is the same. So hit case means that the data is found in the cache. So, and then as we learned in chapter 4, so it will take only one cycle. So it means that in the instruction fetch stage will take only one cycle, as we learned. Also, the memory stage also will take only one cycle for hit case. So you don't need to consider about this case because this is the positive, the good case. Okay, but we need to consider the miss cases. And then I also explained when cache miss occurs, and the processor, the pipeline of our pipeline processor will stall. Okay, so which means that the instruction fetch stage, then the processor try to fetch an instruction using program counter, but this instruction is not found in the cache. If this instruction is not found in the cache, then or we need until the instruction is transferred from the main memory or low level cache. Okay, so which means that pipelines are stored. Okay, then how can we calculate these memory store cycles? So we can simply calculate the memory store cycles using this equation. So the number of memory accesses per program, right? And then miss penalty is the required cycles for one miss case, right? And miss rate. This is the memory store cycles by cache miss, right? The number of memory accesses per program, so which means that is the number of that's the number of memory accesses. And then actually the miss rate is less than 1. So because there are only two cases, and hit and miss. So we need to only consider the miss case. So this rate is the probability of miss. And then we need to multiply miss penalty. That is the required cycles for one miss case. So we can rewrite this equation like this. The number of instructions per program. What is this? This is the instruction count, right? And number of misses per instruction. Okay, so it's a number of misses per instruction. So actually, so we can say this is the miss per instruction, MPI. But we will not learn about this metric, and multiply by miss penalty, the number of cycles for miss case. So we can calculate the memory store cycles like this. Then, but when we discuss about the performance of our control system, then we learned about the CPI, clock per instruction. Then let's discuss about the performance of our processor and when we consider about the cache miss cases. So we will calculate the CPI by cache misses. So this is the example. So this is the example of our program. So instruction cache miss rate is the 2%, and then data cache miss rate is the 4%. So what does that mean? So we have the processor has the level 1 instruction cache. So not to fetch instruction from the level 1 instruction cache, so the instruction fetch stage. Then 2% of request. So actually, the processor needs to fetch every instruction from instruction memory, the instruction cache. So 2% of request is missed. Okay, and then data cache miss rate. So data cache is it's a data memory in chapter 4. So it's a data cache. So actually, the load instruction or store instruction access data memory. Okay, only load instruction and store instruction access data memory. So the data miss rate is 4%. Okay, so 2% and 4%. So actually, this is only for load instruction and then store instruction. And the miss penalty is 100 cycles. Then base CPI is 2. So base CPI means that for the ideal cache case, so which means that every access to cache is hit. This is the ideal case, right? This is the best case. So which means the base, let us assume that the base CPI is 2. And then load and store instruction occupy 38% of 36% of instruction, entire instruction. Then how can we calculate the So increase the cycle by cache miss. Okay, so there are two kinds of caches in the process architecture. So instruction cache and then data cache, the level of cache. Okay, so for instruction cache, we can calculate the miss cycles like this. So what does that mean? So actually, every instruction, processor needs to access instruction memory, right? Processor needs to access instruction memory for fetching instruction, right? So actually every instruction, so 100% of instruction need to access instruction cache, and miss rate is the 2%. So 2% of instructions encounter cache misses for instruction cache, and the miss penalty is 100. Okay, so equation is like this. So increased cycles by instruction cache misses is 2, right? So every instruction 1, and then miss rate multiplied with miss penalty, so 2. So this means that this is the clock cycle increased by instruction cache misses. Okay. Then how about the data cache? I said that only load and store instruction access data cache, right? So 0.36, 36% of instructions access data cache, right? And what is the data cache miss rate? It's 4%. So 0.04, and then this penalty is the 100. So it's the 1.44. So 1.44 represents the increased clock cycles by data cache misses. Okay, it's obvious, right? So the base CPI is the ideal case, so which means that so this ideal case means that when the cache is accessed on the with all accesses to cache are hit cases. And then because of cache misses, the clock cycles will be increased. So we can calculate the increased clock cycles like this. So by instruction cache misses, the two clock cycles are increased. And then by the data cache misses, and then we need to know that the data caches are accessed by only load and store instruction. So this is the percentage of load and store instruction multiplied by miss rate, and then multiplied by this penalty. So this is the ideal case is 2, the CPI is 2, but CPI is increased by instruction cache misses. So it's increased by 2, and then also the CPI is increased by data cache misses. So actual CPI becomes 5.44. Okay. So actually the ideal CPU is 2.72 times that's the actual actual CPU. So which means that the cache misses are considered. So in this example, we can know that because of actually cache performance is very critical for the performance of processor, right? So ideal CPI was 2, but because of the cache misses, the CPI is increased by 3.44. It's larger than the ideal CPI. Right. So that's why the cache performance is very critical for the performance of processor. Also, we can consider other metric called the average access memory access time. So average access time of cache. So this metric is called the average memory access time. It is called the AMAT. Okay, AMAT. So we can calculate the average memory access time like this. So hit time plus miss rate multiplied by miss penalty. So average memory access time is that, oh, this is the cache. Okay. Actually, when the processor access cache, then it will take time. Well, so hit time means that when the cache hit or the cache hit cases, the data is returned from cache. Okay, this is the base access time. And then the hit time. So this is the hit time. But when the cache miss is detected, then the request is given to the low level cache, like the L2 or memory. So this is the additional time for cache miss cases. So average memory access time is that, and when the processor access this cache, then average memory access time represents the average memory access time. So it means that when the processor can receive data from cache. Okay, so average memory access time represents the time required for receiving data from cache. Okay, average time for receiving data from cache. Okay, so we need to just consider the hit cases or miss cases. But as you can see, we just add hit time 1 for every case. So it is because firstly, the processor needs to check cache. Okay, needs to access cache, right? Then cache returns the two different results. The hit result. So for the hit case, the cache returns the data. But when the processor accesses cache, then the data is checked in the cache. But in the miss case, so the hit time is consumed, and then for the miss case, the additional cycles are also added because the data should be fetched from the low-level cache or memory, right? So that's why when we calculate the average memory access time, we just add the hit time. So this is actually the main access time, the default access time for cache. Okay, default access time. And for the miss case, this amount of cycles are included in the default access cycle. Okay. So this is the average memory access time. So how can you calculate? This is the example. The CPU has the 1 nanosecond of clock period, and then hit time is the 1 cycle. So which means that so it will take 1 cycle when for the hit case, the miss penalty is the 20 cycle, and the miss rate is the 5%. Then calculate the average memory access time for this cache. So sometimes the hit time can be less than can be less than this clock period, such as maybe the heat time can be 0.8 nanosecond. Then how can you calculate the heat time, the heat cycle? So sometimes some students are confused about this hardware design, this hardware design. So, for example, actually the access time, the access latency is can be provided like, this is the cache, can be provided like the 0.8 nanosecond. So actual access time, not cycle. So, which means that the cache cache can be fast. Cache is faster than the clock cycle actually. So this is the heat time, the access time, so 0.8 nanosecond. So we can provide the heat time like this, but clock cycle is the 1 nanosecond. So it's a clock period. Then how can you calculate the heat time? So even though the heat cache access latency is less than the clock cycle period, so it's a 0.8 nanosecond, but we calculate the heat time. So actually this is the cycle of the one cycle, not 0.8. It is because even though this access latency is less than the clock cycle period, this processor will take one cycle for accessing cache, right? Because this is the digital system, and then every hardware component completes its operation within one clock cycle. So, which means even though some components are very fast, so some components complete the required operations so faster than the one clock cycle, the 0.5 nanosecond. But because this is the system, the processor needs to wait until the end of clock period. Okay, so it's a synchronized. So even though the access latency, the default access latency can be shorter than the one clock period, but we need to think that for this case, processor consume one cycle. So which means the heat time is the one equivalent to 1 nanosecond. Okay, one cycle. And then miss rate is calculated by the miss rate multiplied by miss penalty. So in this case, the miss penalty is the 20 cycle, and then miss rate is the 5%. We can calculate like this. So this is the average memory access time. It's the 2 nanoseconds. So it's equivalent to the 2 cycles. So what does that mean? On average, when instructions access cache, a single instruction consumes 2 cycles for accessing this cache. Okay, this is the definition of average memory access time. So average memory access time represents the average cycle required for accessing cache for every instruction. Okay. So just memorize this equation. Average memory access time is the peak time what miss rate multiplied by miss penalty. Okay. So So in this example, we learned that the performance. So actually in chapter 4, we did not consider about the cache miss cases, but actually in the actual CPU, then we need to consider cache miss cases. And then we learn the performance, the CPI. The performance will be degraded by cache misses like this. Okay, so we need to remember that when cache miss is encountered, then pipelines need to be stored, so cycles are wasted. So we can calculate the CPI, the increase to CPI by cache misses. Also, we also define another metric called the average memory access time, that's called the AMAP. So we can also calculate the average memory access time for each cache. Okay. So, and then, so now I will explain another aspect of cache organization. It's called the associative cache. Associative cache. So, what is the associative cache? What is the associative cache? So if you are interested in a CPU specification, then you can check the some specification of the Intel CPUs. Then you can find that level 1 data cache. The size is the 16 kilobyte and 8-way. So in this example, the size is the size of cache. Well, it's obvious. So it's the size of data that can be stored in the cache. It's the 16, which means that the level 1 data cache of the Intel CPU can store 16 kilobytes of data. Then what does that mean? 8-way. This 8-way represents the associativity of cache. So this is called the associativity. Okay. So 8-way. So this number 8 represents the associativity of cache. Then what does associativity mean for this cache organization? So in the previous class, we learned about the cache organization. And what I said, so this cache is the direct mapped cache. What is the direct mapped cache? So when we learned about the cache organization, so this is the cache block, okay, cache block. And then this one cache block is mapped to the different addresses of main memory, right? Do you remember? So which means that this is the address, and then we use the part of address as the index of cache, okay? So the index of the cache, and then which means that if data has the same index field, okay, then this data field, these data spaces are mapped to the same block of the cache. Okay, this organization is what we learned in the previous class. So which means we can use the part of address field as the index of cache, and then if data space exceeds the same index number, and these data spaces need to be allocated to the same block of the cache. Okay, that's what we learned about the cache organization. Then we can imagine the worst case, like the bad case. What does that mean? So when this data is registered by a processor, then this data block need to be allocated to this cache block, of course. And then let us assume that in the next, for the next load instruction, the next instruction requests this data. But what's the problem? This data space, this data block need to be allocated to the same cache block. Then what should we do? Because, this target cache block is already occupied by previous request, but the current request also needs to store this data block in the same block, same cache block. So this is the limited space. So the previously occupied block need to be evicted from cache. Right. But the worst case is that the cache has the many blocks, but the load instruction requires the several blocks. But the worst case is that several blocks should be mapped to the same cache block. What's the problem? Even though this cache has the many other blocks, these many other blocks cannot be used for allocating these many requests, because these blocks are mapped to the same cache block. So that's the problem. That can be the problem. So this is the worst case scenario, but they can be the problem of the cache. So the problem is that even though cache has many blocks, but the multiple blocks need to be allocated to the same cache block. So cache spaces can be waiting. So I said this is the worst case. So which means that it's not the normal case, but it can be possible, in our program, in our application. So how can you solve this problem? So I define the problem. So what is the problem? Even though cache has many spaces, which means many blocks, many empty blocks, but because of this mapping policy, it's called the direct map policy. Because of the mapping policy, so many requests need to be mapped to the same cache block. So which means if we can avoid this scenario, this case, then we can improve the cache performance. So which means that we can increase the associativity of cache. So there are several kinds of associative cache. The first associative cache is the fully associative cache. So fully associative cache means that. So when I explain about the worst case, the problems of our cache organization, the problem is that multiple memory blocks need to be stored in the same cache block. So which means if we remove this restriction, right? if we remove this restriction, then we can store these multiple memory blocks in the any empty blocks of cache. Right? Understand? So this is the certain restriction. So it's a mapping policy. But if we just remove this mapping policy, then we can store any memory blocks in the any empty blocks in the cache. You understand? So this kind of cache is called fully associative cache. So fully associative cache means that there are many cache blocks, and then so memory has also many data blocks, and the data is requested, and then this data can be stored in any blocks of cache. This kind of cache is the fully associative cache. So the benefit of a fully associative cache is that cache is the cache block space is not wasted by mapping policy. You understand? Because the memory blocks can be stored in any blocks, any lines of cache, okay? So we do not waste the cache space due to the mapping policy. This is the fully associated cache. But what is the disadvantage? So this is the very, so I said, oh, this is a fully associated cache. We don't need to waste cache space by mapping policies. But what is the disadvantage? It's expensive. So it expensive means that it requires more hardware resources. Okay, it's expensive. The cost is high. So performance can be higher than the other caches, but it's expensive. So, and then direct map cache is the what we learned, so which means that the set index of the cache is decided by the part of address, and then which means this block can only store the many memory blocks are mapped to is one cache block, but actually this is called the set. So another possible solution is the n-way set associative cache. The fully associative cache means that the data block can be allocated into any space, any cache block. But n-way set associative is the intermediate solution, which means that many memory space can be mapped into this cache block, but this cache block can store up to n blocks. Okay, so that's this n is equivalent to the n-way of n. Okay, so n-way, and then actually this is called the set. Okay, so what does that mean? The cache set, the cache line. No, a single cache set, like the direct map cache we learned, multiple memory blocks can be mapped into the single cache set. But in this single cache set, we can store multiple blocks. Okay? What's the benefit? So in the direct mapped cache. So in the previous class, we learned about the direct mapped cache. So direct mapped cache means that the one cache set, only one block can be stored. Okay. So, and then I also explain about this advantage of direct mapped cache. So which means, so one, oops. So 1 and 2. So 1 is accessed and then 2 is accessed. Then the 1 should be evicted from the cache. That is the disadvantage of direct mapped cache. But if one set can store 2 cache blocks, it's the two-way set associated with the cache, then in this case, 1 can be allocated in the cache first, and then 2 is also allocated in the cache. But so this one memory block number 1 is not evicted from the cache. Why? One cache set can store multiple blocks. Understand? So I said that if a single set can store up to n blocks, then this cache is called the n-way set associative cache. Okay? So what does it mean? So in the example, so in the previous example, I said that in the Aeron cache is the 8-way set associative cache, which means in the Intel, so in the Intel CPU, this level of data cache can store 8 blocks per one cache per set, per cache set. Okay, so it's called the n-way set associative cache. So n-way set associative cache is more expensive than direct mapped cache because we require the n comparator. So which means that actually, how can you identify the memory block? So we can just compare the tag. Okay, tag stored in the cache. But in the fully associative cache, the memory blocks can be stored in the every cache line. So which means that we require comparator per entry of the cache. Okay, so that's very expensive. But if we use the n-way set associated with the cache, so in the one cache set can store up to n blocks, which means we require n comparator. Okay, it's less expensive than fully associated cache. Okay. So usually the commodity CPUs do not employ direct mapped cache because of this problem. Direct mapped cache exceeds the higher miss rate. So in order to reduce the miss rate, we can use the n-way set associated with the cache. But we can know that fully associated cache is can exceed the highest performance, which means that the miss rate is this rate of the fully associated cache is lowest, but it's expensive. So usually we use the n-way set associated cache. I will explain the reason later. Okay, this is the example. So in this example, this cache has the 8 blocks. Okay, so it's a block number. So, and then direct mapped cache means that in the one cache set contains the one block. That is the direct mapped cache. So this set is in the address field. The part of address field determines the set index. And then if the memory blocks, so memory blocks that has the same set index is mapped to the same set of the cache. But in the direct map to cache, one cache cell can store only one block. Okay, so that is the direct map to cache. So we can just compare one cache. And then set associative cache. The definition of a set associative cache is that the one cache set can include the n blocks, the multiple blocks. So this example is the two-way set associative cache, which means there are four sets, then each set can include two blocks. So set number 0 includes the two blocks. Okay, it's the same. You can put the same data field that shares the same set index is mapped to this set, but this set can include two cache blocks. Okay, this is the two-way. And then fully associated cache, there is no set, because actually in this example, fully associated cache has the only one set. Okay, which means that the memory block can be mapped to the any blocks in the fully associated cache. So which means fully associated cache has only one set, and which means you need to check the every tag of every block to identify the data stored in the fully associated cache. Okay, so this is the example of the associative cache. So actually, if we see that this cache, the cache size is the same, right? So each cache has 8 blocks. Okay, cache size is the same, but we can apply different associativity, like direct map or set associative cache or fully associative cache. Okay, so let's see the example. So in this example, we just explore the performance of associative cache. So the first example, we just compare the behaviors of direct map cache and then two-way. Two-way means that one set includes the two blocks and then fully associative cache. And then this is the block access sequence 08, 06, 8. So in the direct map cache, and then firstly the cache is empty. So block address is 0, the cache index is 0. Okay, and then cache has only 4 blocks. So and then this is the block address. So which means in the last 2 bits determines the index of the cache. So the block address 0, the cache index is 0. So this is miss because the cache is empty. And then the block address is 8. So 8 is 0, 1, 0, 0, 0. And then so which means the index of cache is 0, 0. So cache index is 0. So what does that mean? Oh, we request the block address 8, but this data is not found in the cache, right? Because the cache has only block 0. Okay, so this is a miss. But this block need to be allocated to the index number 0, right? Understand? Index number 0. So which means, oh, this block need to be allocated into this index. Okay. but this index is already occupied by memory block 0. Right. So in this case, this memory block 0 is evicted from the cache, right? Because it should be occupied. And then memory block A is newly located. Okay. And then 0. What's the problem? So data block 0 is already evicted from the cache, even though this block is previously accessed because of the direct map, because we use the direct map cache. This block is evicted from cache. So which means we cannot find this block because when the set index 0 is checked, this set includes only memory block A. Understand? So this is also miss. And then block address 6, so which means the cache index is the 2 because 6 is the 110. Okay, so memory block 6 is allocated in the cache index 2. The 8 is also missed because for this request, memory block 0 is allocated to the cache index 0. Okay, so what does that mean? In this example, we can find temporal locality. So temporal locality means that 0 is requested and 0 is requested again. So temporal locality is observed. So another temporal locality is the 8 and 8. Okay. So 8 is requested, and then in the future, the 8 is re-accessed. So we can observe temporal locality of the data, but this temporal locality is not utilized by cache because of mapping policy, so direct map cache. Okay, this is the worst example. But this example explains how the temporal locality is not utilized by direct map cache. So another example is the two-way set associative cache. So in the two-way set associative cache, one set includes the two cache blocks. And then I said this cache has 4 blocks, so which means this cache includes only 2 sets. Understand? Because the total number of blocks is 4, and then each set includes 2 blocks, which means this cache has the 2 sets. Okay, so it's a two-way set associated with cache. So one set includes 2 blocks. So that's why this is the two-way set associated with cache. So which means in the block address, the LSB 1 bit is used for index of this cache. Understand? Because this cache has only 2 sets. So let's see the behavior of cache. So the block address 0 is equal to miss because the cache is empty. 8. So 8 is firstly accessed, so indexing of cache is 0 because the block address is 1 0 0 0. So this is the index of cache, so it's 0. So in this example, this cache is the two-way set associated cache. So memory A can be allocated to the empty slot of this set, target set. So in this example, the set 0 has the 2 blocks, and then the first block is occupied by memory block 0, and then this set has the empty block here. So memory block A is allocated to the empty block. And then memory block 0 is not evicted. Understand? And then 0, oh, is a 0. So in this case, oh, memory block 0 is not evicted from the cache. So memory block 0 can be found in the cache. And this event is a hit. And then 6. So, and this block address is 6. And block address is the 110. The 6. So index number is 0 here. So in this case, all blocks of cache are already occupied. So one of these blocks need to be evicted from cache. So which means, so if we use the self-associative cache or fully associative cache, then we need to decide which block need to be evicted from the cache if the target set is already full. Okay, so this is for the cache replacement policy. So in the direct method cache, then one set has only one block, so we don't need to consider about the replacement policy. But if a target set includes the multiple blocks, then we need to decide which block need to be evicted. So actually we frequently use the LRU policy. The LRU means that least recently used. So least recently used. So which means that least recently used block is evicted from the cache. So in this example, which block is least recently used? So memory 0 is hit, so it's used, right? So among these two blocks, memory block A is least recently used, right? So in this case, memory block A is evicted from the cache. Memory 6 is duly allocated to this block. It's replaced. Okay, so this means and then A is not found. So which means so the index number is also 0. So also we need to decide which block need to be evicted. So in this example, the memory block 6 is recently used. So this block, memory block 0 is evicted, and then memory block A is allocated in this cache set. So compared to the direct method cache, the direct method cache, all accesses are missed, but the two set associated cache, we can find one hit. And then fully associated cache does not have set. Okay, because the memory blocks can be allocated to any blocks of a cache. So in this example, you can find for no set here because fully associated cache has only one set. So 08000806A. So it's the first miss, and then the 8 is also miss, but 8 is allocated to the empty block of the cache, and 0 hit, right? And 6 can be also allocated to the empty block of the cache. And then 8 hit, okay? Because the 8 can be found in the cache. So this example shows that if we use the fully associative cache, then we can use the blocks of cache, so space of cache more efficiently. So we can reduce the cache miss rate. But as I mentioned, fully associated cache requires the many comparator. So the number of comparator is equivalent to the number of cache blocks. So it's very expensive. So then in order to increase the performance of our CPU, then you may think that, oh, we can use the fully associated cache. But it's not always true. So this is because for the normal application, so this slide shows the miss rate by associativity of cache for the SPEC 2000 benchmarks. Okay, so for that data cache. So if we use the one-way cache, so which means this is the direct mapped cache because one set contains one block. So we can find that if we use the one direct mapped cache, then cache miss rate is the 10%. We use the two-way set associated with cache, then it's 8.6%. 8.3, 8.1. So actually, the hit rate, because the hit rate is the performance of CPU is influenced, is a proportional, maybe is influenced by hit rate. If we just consider the hit rate of the cache, and this is the set associativity, then hit rate of cache is not proportional to the set associativity. Actually, the hit rate is saturated. So you can find this example. But actually, this example shows the miss rate. you know, the hit rate is the 1 minus miss rate, right? So even though we increase the set associativity of cache, the hit rate is saturated. So which means we don't need to use the expensive fully associative cache because the hit rate will be saturated. That's why we do not use the fully associative cache in the CPU. So usually we use 8-way or 16-way set associative cache for our caches. So, but usually we use the 16, the high set associative cache, the 8-way, so low level cache, last level cache. So we use only 8-way or even 4-way cache, the level 1 or level 2 cache. Okay, because the hit rate is saturated by set associative. Okay. So this is the organization of the cache. Okay. So this is the address, and then we can use the part of our address as the index field. And then this field shows the 4-way set associative cache. Okay, and then this set associative cache has the 256 sets. Okay, 256 sets. And then this is the block offset. So the size of one block is the 4 byte. And because this is the 4-way set associative cache, one set includes the 4 blocks. Then there are 256 sets. So because there are 256 sets, we can use the 8 bits of address field as the set index. And then in one set, we can store 8 blocks. And then as you can see, each block includes the head area and control bits at the LED bit. So using this index field, the cache is accessed, then we can read the 8 different data and text and valid bit. And then using the four different data, text, and valid bit from the is 4 cache blocks of the same index. Okay. So then we just compare these 4 tags with the tag part of the address. Okay, you can find the 4 comparators here, and then also we need to check the validity of block. Okay, the one of these blocks hit, then it's cache hit. Then we can select from the data from 4 blocks of this cache set. This is the organization of the set associative cache. So compared to the direct match cache, here you can find the direct match cache only one. You can find the one tag, one data, and one valid. But in the set associated cache, you can find the multiple blocks. Multiple blocks are read from the target set of the set associated cache. Okay. So I will stop here. So in this class, so in today's class, I'll explain about the performance of a cache. Also, I also explain about the set associated cache. Any questions? Okay. Thank you for your attention. Then see you in the next class. 감사합니다.